Okay, so life in the clouds of Venus. And this follows up on the announcement just a couple of months ago of the idea that a detection had been made of a biosignature of a gas in Venus's atmosphere, a gas called phosphine, which is a very unusual chemical, which we'll talk more about as we go through. And we'll talk about how that was made, how that detection was made, and also about why we think it's got some sort of biological origin. Very interesting papers on the subject, which I've read and researched, and also there's a couple of videos that you can watch on YouTube by the original authors being interviewed. So there were some people from Cambridge, from the IOA, Dr. Paul Rimmer, and Sarah Sagan, you may remember. She's been and given talks to us at the IOA before now. And Jane Greaves, who's a visiting professor at Cambridge as well, was involved. So a lot of Cambridge involvement in this one. So life in the clouds of Venus. Well, first of all, this is a lovely picture of Venus, our neighboring planet, and nearly the twin of the Earth in terms of size and mass. I think the Earth is about 8,000 miles in diameter, and Venus is just about 200 miles less, so almost an insignificant difference. And this lovely picture of the clouds with that classic V shape that you tend to see on the clouds of Venus. Another picture of it here, taken with a different camera from up close. One of the orbiters took this one. So as I said, about the same size as the Earth, a little bit less diameter and therefore a bit less massive as well. But crucially, it's closer to the sun. And being closer to the sun, we'd expect it to be hotter. Well, the question is, how much hotter? And I get my GCSE students to work this one out for me. It's 70% of the distance. We say the Earth is at 1 astronomical unit. Venus is at 0.7. So by the inverse square law, we can multiply 0.7 by itself and get 0.49, which I'm going to call a half. And so the inverse nature of that means it receives twice the heat that we do. It's a very neat calculation. But that doesn't mean that we should expect it to be double the temperature, because temperature goes with the fourth power of the heat. And so actually the increase in temperature would be expected to be the ratio of the fourth root of 2, which my calculator tells me is 1.2 approximately. And so we'd expect a 20% increase in the temperature. Now you've got to work in kelvins, in absolute temperature, and the Earth is about 20 degrees C, which is 293 Kelvin. And so working that out, you should expect Venus to be about 384 degrees Kelvin, which is 75 degrees C, which is certainly pretty hot, getting on the way to boiling point of water. But in fact, it's much hotter than that, as we shall see. And the reason, of course, is because it's suffering from the greenhouse effect of its atmosphere. It's a very thick atmosphere, 90 times the density of our own. And what's more, 95% of that thick, soupy atmosphere is made of carbon dioxide, which we're all very worried about here on Earth from the point of view of it giving too much of a greenhouse effect. So this huge amount of it, and the fact that it's CO2, means it traps a vast amount of heat, and the surface temperature is actually raised not to where we calculated it to be at about 350, but actually more like 450 degrees centigrade. But talking about that as just the surface temperature doesn't really tell you the whole story of what's going on. What we really need to look at is how the atmosphere behaves from the surface up to high altitude. And this is a chart of the temperature in degrees Kelvin at the bottom there on the surface. So it's 750 Kelvin, 450 degrees C roughly. But the temperature drops, according to this blue line, quite quickly. reaches a minimum and then starts to get hotter again. And the reason for that is as the gas gets thinner and there is less to protect it from the direct radiation of the sun, it starts to be warmed. The middle layers are blocked by the slightly higher layers being hazy, and so they are at a lower temperature. And then, of course, you get down into the thick layers where the greenhouse effect kicks off and causes that runaway heating. And as in the graphic here, there's a thick layer of cloud down in the mid layers of the atmosphere. Now, the altitudes there are in kilometers, and on Earth, we call 100 kilometers the Kármán line, which is where you have to fly to get your astronaut badge. Now, of course, Venus's atmosphere, being much thicker, extends to much higher altitudes at worthwhile pressures. And so it's we have to go much further up, really, before we get to anything that approaches that of a vacuum. Now, I've talked about the greenhouse effect. Here on Earth, we get warmed by it. The rays of the sun, both long and short wave, so visible and infrared, come into the atmosphere, and some of the infrared can't then get out because it's trapped by the gases in the air. And particularly effective gases are water vapor, H2O, in the atmosphere, methane, CH4, and carbon dioxide. And between them, the three gases that we have in our atmosphere are keeping the Earth warmer than it would otherwise be. Based on that heat calculation that we were looking at earlier, you could work out the temperature you'd expect the Earth to be, and it would be about 20 degrees C lower than it is now if it wasn't for the greenhouse effect. So it's a good job we've got one. The problem is that we're adding to it, and we really don't want to make it get any hotter. Now, if you look at the sort of comparison between the two planets' atmospheres, the same sort of processes are going on. We've both got incoming sunlight and reflected sunlight, and a lot of that is bounced away, especially by the reflective clouds of Venus. But the infrared light tends to be able to penetrate through the clouds, warms up the ground, and then can't get back out again at even longer wavelengths, as it's the same process but just magnified. So we don't really want that to happen to us and for the whole thing to run away. If we add too much to our greenhouse effect, we could suffer the same fate as Venus if we're rather careless with our planet. But that's another story. What it does point to, though, is that in the deep past, by which I mean perhaps 2 billion years ago, it was quite likely that Venus looked a lot like the Earth, with substantial amounts of liquid water and a sort of much more pleasant aspect to it. It would have been quite warm. It would have been a minimum of the sort of temperature we calculated, 70 degrees C, but nevertheless not reached boiling point. But what happened was that gradually volcanoes gave out too much carbon dioxide and a runaway greenhouse was triggered. The water then evaporates from the oceans into the atmosphere, and water is actually an even better greenhouse gas than carbon dioxide is. So once the water is in the atmosphere, the temperature goes skyrocketing and everything gets completely out of control. That's then followed by another process which actually dehydrates the planet. And the reason for the dehydration is that Venus spins very slowly on its axis. It actually takes 245 Earth days for Venus to rotate once. And as a consequence, there's not enough of a dynamo effect inside the planet to generate a worthwhile magnetic field. It has a very, very weak magnetic field compared to that of the Earth. That lets the solar wind in, and of course the solar wind's even stronger at Venus than it is at the Earth, so it's a double whammy. And what happens with the solar wind is that it takes apart the H2O molecules in the atmosphere, leaving the oxygen behind, and the hydrogen, it then escapes to space. Being very light, it can be torn away and blasted off into space, never to return. And so gradually the amount of hydrogen in the composition of the atmosphere is depleted, and a lot more oxygen is left behind. So what about the weather on Venus then, down in that low part of the atmosphere beneath the clouds? Well, it rains there. Mostly rains 95% pure sulfuric acid. That's a consequence of the amount of water that's left mixing with sulfur dioxide and spare oxygen from the depletion process, and the sulfur dioxide from the volcanoes to make H2SO4, sulfuric acid, battery acid, as we use in lead acid batteries. And so it rains droplets of pure, almost pure sulfuric acid out of the clouds at around about 30 kilometers altitude. But that never reaches the ground, because as the raindrops fall down towards the ground, they get hotter and hotter. Remember that temperature is going up all the time as you get nearer the surface. And so if in fact the raindrops of sulfuric acid boil away back to vapor before they make it to the ground. So it doesn't really rain on the surface. Now, another surprising discovery was the appearance of snow on the mountain tops. There's a picture here. It's actually a composite picture of different wavelengths involving radar, showing snow on the peaks of the mountain tops on Venus. But this snow is not made of water ice snow that we would use and throw snowballs at each other with. It's actually made of a ghastly mixture of heavy metal compounds involving lead, bismuth and tellurium combined with sulfur. So things like bismuth sulfide and pure tellurium and other things snow out onto the mountain tops. And this was discovered by these two people here, Professor Bruce Fegley and Laura Schaefer, who are standing there talking about a meteorite, in fact, but nevertheless, they discovered that it does snow this ghastly heavy metals. So not somewhere to book your skiing holiday there either. Now, we've had a number of probes that have been sent to Venus to inspect it. The Americans have sent one or two flybys, but it's the Soviet Russia that really led the way in exploring Venus with a whole series of probes. And this is just one of them, the Soviet Vega 1 probe. This is just a model here, but it's was on its way to visit Halley's Comet in 1985, and it carried with it a large deployable balloon which could be dropped into the atmosphere and measure the atmosphere as the balloon gradually descended. But as with all probes, it was eventually doomed to be destroyed by the hellish conditions. Here's a few of the pictures that we have of the surface of Venus taken by the Soviet landers. The Venera probes 1 through 13 were all sent there, and just a few of them made it to the ground and managed to take a few quick snapshots. And you can see the rim of the spacecraft here, or the lander, with these armored teeth around the outside of it. This thing is built out of battleship technology to survive the 100 atmospheres pressure and the temperature, and being soaked in battery acid on the way down. These things here, these strange horseshoe arrangements, these are actually the lens cap from the camera that's been ejected. And then this was a sampling arm that deployed outwards to try to sample some of the rock. But really, those are the only photographs that we have of the surface directly, and that we've had these for probably 30 years now since they were first produced. Early ones were in black and white. These are just a few that are in color. And it shows that barren, rocky surface. I think the record was about 35 minutes for a probe being on the surface of Venus before ceasing to function. But the subject of this is not really the hellish conditions on the surface. It goes more towards the idea of things in the atmosphere. And this goes all the way back to a proposal by the great Carl Sagan, very much a visionary of all things astronomical. And along with Harold Morowitz, he put a paper out which was published in Nature, so it was taken very, very seriously. And it talked about the possibility of life in the clouds of Venus. So he said it's possible that life arose under moderate conditions on the surface of Venus early in its history, as we were talking about. But then as outgassing, that's the volcanoes adding carbon dioxide into the atmosphere, surface temperatures rose and the surface became more inclement. That's a very mild word for the hellish conditions that there are now. But then he says organisms may then have emigrated to the clouds and there be awaiting the first biological experiments to be performed in the vicinity of the Venusian clouds. So, in other words, waiting for us to discover them. And it's not an entirely crazy suggestion, because when you look at the conditions in that middle layer, it's really still quite a dense atmosphere. It's around about 1 atmosphere of pressure up there at 60 kilometers. We would call, that would be a thin vacuum from our point of view at that height on Earth. But on Venus, the pressure has just dropped to a much more moderate level. And so very much a temperate zone in that middle region. And some artists' impressions for you of the sort of things that Carl Sagan's ideas of this temperate zone led to. I'm not saying these are real, but the idea of some sort of sky jellyfish floating around with these huge balloon envelopes is the sort of idea that astrobiologists have considered for some of these atmospheric regions. And maybe the creatures can control their altitude by inflating or deflating their balloon envelopes and changing height when they need to, and so forth. And this idea has not only been suggested for Venus, but it was also suggested for the planet Jupiter. And in fact, this particular piece of artwork is representing the sky jellyfish of Jupiter, which of course we've got no evidence that they exist, but it's entirely plausible, I suppose. And so the idea would be that perhaps the clouds of Venus might look something like this. Who knows? We really haven't explored. And until we gain the knowledge, then it's anyone's guess. But wouldn't it be exciting to actually have a photograph rather than this lovely artist's drawing showing something like this going on another planet? Well, for the purpose of this talk, we have to understand a little bit about how they made the measurements that led to the paper. And it's all about using sub-millimeter astronomy. What do I mean by that? Well, we have the electromagnetic spectrum laid out here from visible light in the middle, around about here, which is about the right size to be able to just see bacteria and single-celled organisms. The wavelength of light is about the same as the size of such creatures. You can't see very much detail in them, but you can just about tell that they're there because they're on the same order of size as the wavelength. Go to longer wavelengths, the needle point is about the same size as infrared radiation, and then down through microwaves, through sort of the size of insects. We cook with our microwave ovens, the wavelength's 12 centimeters, and then down into the shortwave radio, about the size of a human, or long wave radio down here. And so there are some wavelengths around about 1 millimeter in length, somewhere in here, just near the sort of short end of this microwave region, that are the ones we're interested in. And of course, at the other end, I should mention, once you go to shorter wavelengths, you get to the size of atoms and molecules, and even to the atomic nucleus with ultraviolet, X-ray and gamma rays. So we had a couple of space telescopes that have been very interested in these millimeter wavelength radiations, and there's SWAS from 1998 and the Herschel telescope in 2009. SWAS was looking at 540 to 610 micrometers, so that's half a millimeter to 0.6 of a millimeter, and Herschel a wider range, actually, from somewhat shorter wavelengths going further into the infrared. But you can see they're wildly different from what the human eye can detect in the visible there. And the Herschel telescope was quite a big one. It had a 3.5 meter mirror, I think was one of the largest mirrors to be deployed in space, even twice the size of Hubble, and will only be exceeded once we get the James Webb telescope up there. And so apart from those satellites, we've had to try and do this from the ground. And the problem with doing astronomy from the ground is being able to see through our own atmosphere, first of all. But you can see that there is a convenient gap here in the obscuration of the incoming waves. The visible light makes it all the way to the ground. So does a lot of the radio. There are some gaps in the infrared, but this particular one, this is the millimeter band. And perhaps at ground level, you lose about 25% of the radiation. And that's just about tolerable. But of course, you don't have to build your observatory at ground level. You can stick it on a high mountain and get up to a level which is tolerable. All these other short wavelengths and ultra long ones, and most of this infrared bit here don't get through at all. So you need to go to space for that. So if we zoom in on that a little bit, you can see the sub-millimeter gap. The amount that gets through is definitely worth looking at in this millimeter range. One way of doing it is to put your telescope receiving apparatus on an aeroplane, and this is Sophia. The Americans have a jumbo jet which is based down in New Zealand and flies over the Pacific, and has this large telescope which can do a combination of infrared and sub-millimeter observing. It gets high enough up into the atmosphere to be above most of the annoying problems of the millimeter waves being absorbed by water, in fact, and so gets us a great view. So it was these sub-millimeter waves that were the subject of the detection of the gases on Venus, in particular phosphine, that caused all of the excitement. And there were two telescopes involved in it, the James Clerk Maxwell telescope and the ALMA array in Chile. The ALMA array is at 5,000 meters high. And in fact, our speaker of yesterday was talking about visiting it and needing a doctor because of the thin atmosphere. So it turns out that this particular gas, phosphine, has an absorption band that is nicely placed in the millimeter part of the spectrum, corresponding to 1.123 millimeters long. And that's a specific and highly tuned absorption feature in the spectrum, where phosphine will pick up that energy and it causes the molecule to spin around. It's a rotational transform band of the molecule. And they were able to detect 20 parts per billion of phosphine in the atmosphere of Venus, which doesn't sound like very much, but it's an awful lot more than there is in the Earth's atmosphere. Now, phosphine is pH 3. It's the heavier equivalent, if you like, of ammonia, which is NH3, nitrogen and 3 hydrogens. Nitrogen is in the first row of the periodic table, a light element, and phosphorus is just below it in the same group, so shares many of its chemical properties. And of course, ammonia is a little bit like water, which is OH2 if you write it backwards. It's the next element along from nitrogen, goes from nitrogen to oxygen along that row in the periodic table, the next heavier element, combined with as many hydrogens as you can stick to it, which for that group is 2. And as with ammonia, it won't do you any good if you try and breathe it in. Phosphine is incredibly poisonous and really quite difficult and nasty stuff to work with. But it's not, as reported by some of the press, commonly used as a poison gas in warfare. I saw a report in the press, they were getting it confused with phosgene, which is a completely different chemical and has the formula COCl2. It's carbonyl chloride to give it its chemical name. So phosgene is not the same as phosphine, but that confused some of the popular press. So I said it was discovered initially by the James Clerk Maxwell telescope high up on Hawaii. Looks pretty barren, looks like the surface of Mars really, doesn't it, apart from the observatory building in the middle there. And there are 3 telescopes here. The middle one, this big one, is the James Clerk Maxwell, which has a 15-meter diameter mirror and is dedicated to this sub-millimeter band. And then this is a smaller sub-millimeter band telescope belonging to Caltech, and then the Smithsonian have another sub-millimeter array over here on the right of the picture. So this is definitely where the sub-millimeter action is on Hawaii. And this is the detection that they made. You can see actually when scientists talk about detecting something, we're looking at the spectrum. It's quite noisy and got quite a lot of bumps in, but there is a distinct dip just here at the exact point of interest that they were looking for. And they've fitted a curve to it here to show what the ideal spectrum of phosphine would look like. And it looks quite good. That peak in the ideal spectrum seems to correspond. There's a slight extra bit of width over on this side to this side maybe, but it looks pretty good. So having made that initial discovery, they then managed to get some telescope time on the ALMA array, the Atacama Large Millimeter Array in the Chilean Andes up at 5,000 meters, even better instrument for doing the same thing. Lovely picture of it here with the large and small Magellanic clouds in the sky, those dwarf galaxies that orbit the Milky Way. And lo and behold, they got a very, very similar plot, which is always a good thing. And it's confirming the result very nicely that this detection of this peak corresponding to phosphine in the atmosphere. And so the idea then is that perhaps there are not sky whales or giant jellyfish, but bacteria living in the droplets in the clouds in that 50 to 60 kilometer altitude band, and that maybe they are producing this phosphine gas, and that perhaps they're managing to survive, and some of them will probably get carried away and destroyed high in the atmosphere or baked by falling down too low, but a lot of them might be managing to eke out some sort of existence by circulating in the cloud layer inside the droplets of sulfuric acid, perhaps. A very wild environment, really. But just before we go into the details of why they think that might be the case, let's have a little look at phosphine on Earth. I've said it's pH 3, so we've got the big phosphorus in the middle and 3 hydrogens stuck to it. So if you had super sharp X-ray eyes, that's what you could see perhaps. And it's an interesting chemical. It burns the moment you expose it to air. This has been made in the beaker on the right there, and it continually being made in solution. And then as it gets into the vapor stage, as it comes out in little bubbles, it's immediately bursting into flames with the reaction with the oxygen in the Earth's atmosphere. And so we have almost none of it in the Earth's atmosphere at all, because the oxygen just takes care of it as soon as it's produced. And I've added there that there's a heavier version of it, P2H4, which is even more unstable and usually is what's responsible for the automatic ignition. The pH3, if made pure enough, it will react with oxygen, but it needs a spark. But you usually get some of the diphosphine, the P2H4 in there, that makes it trigger off. And a common source of it on Earth is actually the decay of organic matter. Organic chemistry makes quite a lot of use of phosphorus. It's in phosphates in our DNA, is reliant on phosphates, and a lot of our energy handling processes in biochemistry make use of phosphates in the form of things like ATP, adenosine triphosphate, absolutely vital energy carrier inside the body. But the only place you're likely to see it is out in the woods after dark, in the swampy woodlands. We see sometimes these weird lights in the woods, which were thought to be the will-o'-the-wisp or the jack-o'-lantern, various other names in other parts of the world, seen everywhere, these strange blue lights. And what's happening is that under the water, in the little rotten, fetid ponds, you have organic matter that is decaying in conditions where there is no oxygen left. And it's producing a mixture of gases, methane and phosphine, and a little bit of that diphosphine as well. And then that bubbles up to the surface as marsh gas, and the diphosphine acts as a spark plug and ignites the whole lot. And you see the blue color of the burning methane, but it's actually the phosphine and its analog diphosphine that are responsible for it catching light. So if it was pure methane, it wouldn't happen. It would just bubble up and mix into the atmosphere. In fact, the amounts that we have in the Earth's atmosphere are about 1 part in a trillion, as opposed to 20 parts per billion that they found on Venus. Now, another source, apart from the will-o'-the-wisp, which I'm actually almost loath to mention, is that we get a certain amount of phosphine from penguin farts. Penguins are quite good at producing what we would say is phosphorus-rich white organic substance, and certainly coming with that, you get quite a lot of phosphorus hydride, pH3 phosphine, and there was some research done on there with these maps of where the penguins are and where they found phosphorus, and also where they found phosphine in the atmosphere associated with the said product. Well, what about other planets? Why are we so excited, particularly about Venus? We find phosphine in the atmospheres of both Jupiter and Saturn. It's quite common. Well, the reason you find it in such giant planet atmospheres is because they are so rich in hydrogen. About 3/4 of the planet's atmosphere is made of hydrogen. And this means that the hydrogen is willing to react with anything and everything just to try and sort of even things out chemically. It's a very highly reducing atmosphere, as we would say. the opposite of what we have on Earth, which is an oxidizing atmosphere with all that free oxygen that we have. And Venus's atmosphere is also highly oxidizing because, as you'll remember from the early part of the talk, it lost most of its hydrogen out to space, leaving the oxygen behind. But these giant planets are the opposite. They're highly rich in hydrogen, and so it's no surprise that things like sulfur turn up as the hydride SH2, and phosphorus turns up as PH3. So back to the story of the paper and the phosphine in the atmosphere of Venus. And this is a little bit of a complicated chart here, but what it's really telling us is that the chemists involved in the project did a very, very detailed chemical model of how the different chemical species, all the different types of molecules that are involved, probably about 100 different chemical molecules involved in all of this, would all react together in 1,000 different ways, and I'm not exaggerating, it really is that many, to produce either the destruction of phosphine by oxidizing it back to phosphate, or the formation of it. And in the left-hand chart, this is their estimate of how phosphine would be formed at different heights in the red, and the rate of destruction of it at different heights in the blue. So you can see that once you get above 60 kilometers, it gets destroyed really quite quickly. But down here, it's got much longer lifetime. And you can see, actually, this is a logarithmic scale here with an inverse 10 to the power of, but going from here to here, we're talking about 100 million times longer life in the atmosphere. And so if you combine the rate of formation and the rate of destruction together, you can get an estimate of how much you would expect to find as the equilibrium amount. And that's on the right-hand chart. And this combined graph looks like this. This is the combined level that you would expect according to the height. So there's an interesting peak in it around here in that 40 to 50 kilometers. There's quite an abundance of it. Higher than that, and it's destroyed almost completely, and that's by the ultraviolet light coming in from the sun. But this was certainly the region of interest here. So it could be formed on the ground and make its way up into this cloud layer. But the amount that they found is the final line here. It's much more. And again, when I say much more, we're talking for going from 10 to the power minus 15 to 10 to the minus 8. So 7 orders of magnitude. It's a factor of 10 million times more of it than you would expect, based on just the inorganic chemistry of what was going on. And so the idea is that really they can't account for how much phosphine they actually found by a factor of 10 million unless there is another source of it. And really the only one that they haven't been able to rule out is a biological source, as we have on the Earth. So we have a lot of bacteria on the Earth that produce other chemicals like methane and hydrogen cyanide and other things, and indeed phosphine. It is in fact the gut bacteria of those penguins that are producing the phosphine. So it's not unheard of, and it certainly could account for it. Now, they're very cautious people as scientists. They said it could be a biological source, but they didn't absolutely go out and say we found life on Venus, although that's what the press translated it into, and I'm sure they knew that was going to happen. Now, another paper's recently been published pouring cold water on the idea and suggesting that actually sulfur dioxide in the atmosphere could be responsible for the difference. And turns out it has an absorption band at 1.121 millimeters, which is very, very close to the 1.123 millimeters of the phosphine. And they were suggesting that this was perhaps accounting for that 10 million fold extra abundance of phosphine, because it was in fact sulfur dioxide, which we've always known about. And that if they subtracted the known amount of sulfur dioxide away, then it would mean that the graphs on the previous slide would all line up, and there would be no need for any gut bacteria, shall we say. But just the other day, just to add a twist to all of this, the original authors have hit back and saying they were aware of this sulfur dioxide line, and that it only applies to a rare excited state of sulfur dioxide where an electron has been kicked into a higher orbit, and that such things are very unstable, especially at atmospheric pressures of greater than 1, such as are found in the cloud layers of Venus at the altitudes that they're interested in. This is very much in the same way that the aurora on Earth are formed by the excitation of molecules of oxygen, gives us that green color, and that can only operate and only exist at very, very high altitudes, because it will bump into another molecule if there are any around, and then won't give out the green light. Well, the same thing is true here, that at the pressures concerned, the sulfur dioxide won't exist for very long in the excited state, because it will bump into another molecule and ditch the extra energy without contributing to the spectrum at all. So we're back to maybe the phosphine is there, and maybe it's got a biological origin. So of course what we're going to have to do is go and take a sample and measure it, and this has got NASA very excited in the idea of a return to Venus mission, taking a high altitude balloon and being able to drop a probe down into the various layers of the atmosphere and spend a long time studying the atmosphere at different heights and at different longitudes and latitudes as the balloon moves around. And there's got precedent for this. The Russians tried it, but perhaps with modern technology now, we could build one that was going to survive and really get some very interesting results indeed. And wouldn't it be nice to put a camera on there? I'm sure they will. And so that leads really to the conclusion of this, and perhaps one day in the future, this artist's impression will be possible with a floating sky city. It's got kind of an anchor hanging down into the lower regions of Venus's atmosphere, but the whole thing is pressurized to be able to float through having that property of being slightly lighter than the surrounding super thick atmosphere, and hang out in this temporal zone or temperate zone in the mid altitudes of Venus, and act as a sort of space station or Venus station for scientists and study of the planet. So perhaps one day in the distant future, such a thing will be possible as a sort of outpost to do further research from. And so I'll just bring that to an end there. And if you've got any questions, then do let me know and I'll try and answer them. There's a lot more detail behind the analysis that these people have done. But thanks very much for listening.